Let's start. So yeah, Sumcheck is now widely used in like various DKVMs and stuff. And the main thing we want to kind of prove and verify is this given some polynomial, like multivariate polynomial. So L variate here, and then when we sum over this Boolean hypercube, it's some number, some result. So we can reduce this problem into single claim like this. So naturally, if you naively do this, maybe you need to like open G polynomial at 2 to the L like points and then sum over it in the verifier side to check. But now we can do with the random one challenge at the, and then like open only once at one point. So recap of this protocol is so yeah, you have this, and then you will have to do L rounds, and in each round you will reduce the sum, like number of variables that you're summing over. So like at ith round, we will have like I-1 challenge from previous round, and then we will have one univariate polynomial, and then we will sum over the last like L minus I variables in over the Boolean hypercube. So the result of this sum will be a univariate polynomial over X, right? And then the prover will send this SI polynomial over the evaluation domain. So UD is evaluation domain, and actually I forgot to add here.
I left comment.
Yeah, I forgot to add here, but UD hat is evaluation polynomial, evaluation domain minus the 1 point, single point, because we can derive SI1 from SI0 and previous rounds constant value. Yeah, so we don't need to send this. So it is kind of like a small optimization to reduce the number of points you are sending to the verifier. So maybe very minor stuff. So you can just think of it as an evaluation domain. And so what we want to optimize here is, so typically the initial polynomial, like let's say so we have, let's say, initial values of gx, right? They are usually small values, let's say from a base field. But for security, these challenges are from a larger field, like extension field, for example. And this creates like a big, so for example, in the first round, most of the multiplication will be small value against small value. So it is going to be very fast. And maybe from the next round, it's going to be a bit hybrid and maybe even become large. So it's going to be very slow. So what we want to optimize mainly is about this large. We want to do this few times as possible. So the key idea is, okay, so for the subject to be more generic, we typically can write gx as this. So now gx can be actually polynomial degree of d, but these will all have like a individual degree of 1. So we have multiplication of d polynomials, and so we can write gx as this, right? So it's a more, gx can be up to degree d. So let's say we have this, it's a bit, looks a bit complicated, but yeah, it will just mainly stay in this form. So so gx is of that form. So algorithm 1 is the simplest one. So typically we have, So for each of these polynomials, we have the like evaluations. So the results of these polynomials at each value, each x evaluation domain, and then over this Boolean hypercube, and then yeah. So we have pk at x is same as evaluating this polynomial at x. So we have this array. So if you notice, this array will have each have 2 to the L size. So if L is 20, it's gonna be 2 to the 20, which is like what? 1 megabyte. 1 megabyte. Is it terabyte? No, right?
Depending on the field size, depending on L. So
Well, let's say it's 32-bit, then it's gonna be like 4 byte. So it's 4 megabyte,
yes.
4 gigabyte. Each array is 4 gigabyte.
No. Oh, really?
Yes, if you think about L is 20, then it's 2 to the 20, right?
That's megabyte.
Yes.
So
2 to the 20 is megabyte.
yes,
2 to the 10 is megabyte.
yes,
And you,
yeah, because 2 to the 10 is 10. 10 is almost kilo. So 2 to
right, that's megabyte. Okay, 4 megabyte. Okay. Not bad.
but if you maintain this as an extension field, that's double and double.
Yeah, but actually the first round is gonna be D and in it's in base field, right? So after the first round, it's gonna be halved, so it's gonna be fine, I guess.
But if you implement this, I guess even if it's the first round, I would maintain it as the extension field. Otherwise, you need to allocate again. Maybe not.
But I think also like L can be 30, actually. So in that case, it's gonna be
gigabyte.
4 gigabyte for each poly.
Yes.
So it's gonna be quite big. So anyways, so actually we can compute SI using this formula. So maybe it's good to use board now. So actually the PK1, the first one is gonna be what? Just all the, so let's say we have like, so simple polynomial of 3 variables. And let's say x1 is 1, right? So let's say x1 is 1, then it means just all the monomials. Let's say we have like x3 here. So it's just all the monomials, all these, but with x1 is gone, right? x1 is just 1. And if you put x1 to 0, the second P case, the next one to 0, so it's all the parts without the x1, without the x1 part. So if you subtract this 2, it's gonna be only this left, right? All the parts without x1 is subtracted from the whole thing, so only this will be left. And so it's, so the inner of the bracket P, the first subtraction will give us x2, x3, and then you multiply by u, right? So this is actually basically same as evaluating this at x1 equals u, right? And then the last part is adding this part again back, right? So this is if you set x1 to 0, we have this, and we add it back, but without multiplying by u. So we have the polynomial like ux plus x2, x3 plus x3. So this is basically evaluating at u. So SIU is calculated like that. So this computation is going to be all small because the evaluations are small at the first round, and then we will send the evaluations over all the evaluations of SI, and then receive a challenge, RI, and this is the challenge field, or like it can be large. And then we'll need to update the table because now.
So then do you use a symbol of F for extension field, or do you mix the using prime field and extension field?
Actually, F is only used for challenge field.
I see. That is extension field. That is
Yeah.
extension field. Okay.
And so now the variable of p is reduced by 1, so we will actually halve the size of the table, and using the same formula, right? But at the challenge point, because we replace the first variable by r. We've replaced the first variable by r. So we will use like this and then replace the table. So by this, but now we have our term here. So this is gonna be large values from this round sec 2. So cost analysis in the first round, we need to sum this. I mean, we need to multiply this. So this is a bunch of small values. So this is gonna be d-1 multiplications, I think. D-1 multiplication, and then we have to sum. So we do this product 2 to the L-1 times, right? And then we have D rounds. No, we don't have D rounds. What? We have with this multiplication as well. So we have D multiplication, D times this multiplication by U, and then we need to product D-1 times, and then you have to do it 2 to the L-1 times. So we have this, and then when we update the first round, this is going to be small and this is going to be large. So it's going to be this times small, large multiplications. And then from the second round, we will have just large multiplications only. So this is just some summary of this cost analysis. And then algorithm 2 is a bit slower, but the space is much smaller than the previous one. So instead of storing all these large P, like evaluation table, so evaluation table is 2 to the L. So instead of that, we will just compute from scratch, like just evaluate on the way. So we will use the multilinear extension formula. So this is, so it's a bit different than the complete multilinear extension, because we are just replacing the first I variables. So we are just summing over the first I variables. So it is a more generic case. Typically, we actually, I think, sum over the whole variables. So using that, so the SI is basically, the formula for SIU is this, but then we will use this above EQ extension to write like this. And then so if the last part of Y is U, not U, then it's going to be 0, right? So we can ignore that case, and we will just iterate over I-1 domain, I-1 dimension, and then we'll just hard code U here. And then we will have this, which is same as now we can just omit this, because omit the last part because of the EQ extensions property. So now we just have this, and We will compute it using this value. So now so the main goal of this is avoiding so if you think about it, at each round, the EQ extension's dimension increases, right? So after the first round, it's just 1, I think, and the second round is going to be like 2. So it's going to increase, this computation cost is going to increase every round. So it's typically after L over 2 rounds, we don't want to do this anymore because this is going to be much costly. So we'll instead just shift back to the algorithm 1. And actually, we can even shift back early on because actually computing this is slower than just using the evaluation table. So it's just about, okay, which trade-off you want to do, like at what point you want to like switch to algorithm 1. So the overall, it looks like this.
Oh, question here.
Yeah.
So on the above paragraph, you mentioned that after over 2 rounds is switch to algorithm 1, right?
Mhm.
But if you go down,
Mhm.
so if you see this, for each round, one is the first round, right?
Yep.
Here, then during round I equals to error of 2, it seems that it switched to algorithm 2 because for the leftover rounds,
This one?
yes, follow algorithm 1, which means I2 error of 2 minus 1 using algorithm 1, and after error of 2, is it correct?
Actually, after L over 2, yes, at round L over 2, we will actually start the evaluations. So basically make the evaluation table again, and then use the
I see. I see.
and
I see.
use that evaluation table,
Ah.
and then use the algorithm 1. So yeah, algorithm 1 just use the evaluation table, and this one evaluates. And so this one is going to be large, right? So because of that, and then it's gonna sum. This one has 2. It iterates for 2 to the I minus 1. So there's gonna be 2 to the I minus 1, like small large multiplication, and then D minus 1 large multiplications for product. Yeah. So this is D terms multiplied together, and so there's D minus 1 multiplications, right? And then because there is R challenging here, so it's going to be large values only. So it's going to be large D minus 1 multiplications.
But I mean, the second item was it supposed to be D minus 1 times D times large error? Because if you go above, like, so to evaluate this,
Evaluate which one?
yeah, it's here. So the total cost is D times D minus 1 times 2 to the N minus 1 because D is needed because, yeah, because of that.
Because of this one, right? But we
Yes.
don't have this here. We have only EQ extension. We don't multiply by U there.
I see. I see.
So this one is in here, right?
So only seeing this term that, yeah, D minus 1 large field multiplication is true. Okay.
And the outer sum is iterating to the L minus 1 times. And then the inner, I just sum the inner part.
Mhm.
And then the total is going to be this large multiplications. These small, large, and these large multiplications. And then for evaluating these, we have the small multiplications also, like, but this is small, lower order cost because it's small.
Oh, this
one?
multiplication compute the evaluation is removed.
Yes, because this is Boolean hypercube. This is Boolean hypercube.
U is extension field.
No, U is not extension field. It's the evaluation domain, right? The evaluation domain.
Okay.
So this is also small.
Mm.
It's intentionally small. Yeah.
I see.
Yeah. So these will be all large multiplications, right? So that's why we shift to the algorithm one after some rounds, because this is going to be large. This is the summary. And in algorithm 3, it's going to be kind of messy, but actually I tried to explain. So we start with the same equation of the EQ extension case. And then it's, so if you like just, if you just switch this to, so to explain this, I'll try to explain. So it's just same trick over and over again. So if you understand this, it's going to be simple. So there's product and then sum, and sum is dependent on some y, right? And then this is like some, like let's say some, let's just say a to avoid confusion. Something dependent on a y prime. Yeah. So this is actually a combination of the whole part of it. So if I want to put this like here, so actually if you just expand this sum, it's going to be like what, a y1, like a yn prime, okay, and then you product this, so it's going to be like a y1. This is, let's say, dimension d, right? So it's actually like d multiplications, and let's say it's going to be like maybe the first term is going to be like d times only this, right? You get it? So d times this one, and then the next plus, it's maybe this part is same, a y1 prime, and then a1 prime, and then the last one is maybe a y2 prime, right? Does it explain?
I thought that the product of this summation is like summation times summation times summation times summation, kind of. But it looks like it use sum plus sum plus sum plus sum plus.
This is product.
I see.
This is product. Right? So we will, like, it's just expanding the bracket, right? So if we expand it, like we have like with this to the d, then we have like a1d plus a1 t minus 1 a2
binomials.
Yeah, so plus actually
you need to add d from a1 d minus 1 a2, right?
no.
For the coefficient.
No,
Yeah.
it should be just no. Oh, was it?
Yeah, I think so. DC1, DC2. So the coefficient for the first term,
right.
DC0, DC1, DC2.
Right. So we have right. Yeah. So that's true. But we want to write it in a more simpler way, just because it's true. So what that sum is doing is so the sum, and then the bottom part is what yeah, y prime, but like I wanted to write the same thing but in a simpler one, simple case. So let me think. So there's gonna be two, no, let's say it's gonna be 1, 2, and then this is the index of A, okay? This is the index of A. Oops. 1, 2, and there's gonna be D dimension. So you'll have with Y, no. Okay, Y 1 to D. This. It's the same. Okay. Yeah, kind. No, it's
D and I are independent.
D and I are independent pairs. Oh,
Maybe you can hard code like 0, 1,
actually,
or
I is like what? 2, right?
Yeah.
0, 1, 0. Should be, I guess, just 0, 1, and 2.
Maybe
Yeah.
the above example is hard to understand, maybe confusing for understand this sum.
Actually, now, so it's gonna multiply like a few things. This should be
No, I think the 2 is the like,
no this one.
yeah, I mean, because the square means just there are 2 variables. So just y1 and y2.
No, there should be this is actually about multiplicity of each one. So y1 being 1 means
evaluation of or evaluation of one polynomial, right? There are total D polynomial and D polynomial has 2 variables.
yeah. So this is actually the index, right? It should be including the index. So in this case, I think it should be 1 because we have only 2 variables, right? So it should be. So if y1 is, let's say, 0, then it means we will have a1. If y2 is again 0, it's going to be again a1. And if y2, like etc., right? So if all of them is 0, then we'll have a1d, right? It's going to be a1d. If all y's are 0, then it's going to be a1 times d.
You mean the monomial only, right?
Yeah.
Here
And then,
you don't think about the coefficient of for monomial.
yeah.
Okay.
No, continue.
Okay.
So, and then let's say yd is only the last one is 1, then we have this one, right? Same as this one. And then if only like, let's say y1 is 1, then we also have the same term, right? If y2 is 1, we also have the same term. So it's going to be the binomial coefficient is going to add up like that. So if you just sum over this, it's going to be the binomial extension. So it can be like 0, 0, 0, 0, 1, 0, like, yeah. These are all give us same amount, right? If only this is the index of which.
Yes.
So yeah, so this is actually very large iterating sum because it's all possible values over this. So it's gonna be like d to the power of 2i minus 1. And so the next one is much simpler. So this whole product, we can distribute this product. So it's going to be like this. And then if we expand the EQ formula, we have this. And then if we just switch this to, because this is just multiplication, then, and then if we like do all the multiplications, it's just the exponents are gonna sum together, right? So this is actually, I omitted, but it's gonna sum over d, 1 to d. And then in this here, what am I doing? Switch the order of our, okay, I switched the order, I just switched the order of this outer sum. And then because this part is independent of x prime, we will just move, like we can factor out this product, right? And then we will have this, and then we have this part which is dependent on x prime. So this part is wholly dependent on challenge, and this part is not dependent on challenge, right? So so if we see now this part looks complicated, but actually it's so summing over this, right? And so this is actually can only result in very few possible scenarios. Like the first, like it can sum up to d, right? Each index can sum up to d, and then it will have I minus 1 index variables or index. So if you think about this sum, then it's gonna be only in this, like in this space. So there's only d plus 1, I minus 1 distinct terms, right? So we can also factor out by distinctness. So if you do that, this part is going to be just this sum vector basically, and it's going to each I minus 1 can be up to 10, up to d, and then this part looks a bit complicated, but like this is just all the primes, but this should be constrained that the sum should be equals to v. Now, so if we think about it as, we can think about it as inner product. So this part is like d to the power of I minus 1 vector. And then this part is also like just yeah, you can just think of it. It's just a pretty way to write this in terms of two vector. And here I try to explain a bit more. So because
Is it inner product?
I mean, the outer one is inner product, but like the inner one is a bit complicated, right? So I'll try to explain the left side here. So this can have d distinct value because vj can be only 0 to d, right? So, but j, so this is actually taking also again this kind of similar to this, like and so we have like a d different this value, and then we have to like kind of take all possible combinations of these multiplications again, like because we have to do product over. So if, for example, this is I minus one size vector of D, like each can have D, right? If all of them is 0, it's gonna be like just same 0, right? If one of them is 1, then it's gonna be like all zeros, and then the last one is gonna be 1, kind of like that, right? So the feeling is like that. So it's just this product is called Kronecker product, and it's just like multiplying all possible ways, basically. So this is gonna be what? So this is because each one can have D plus 1 value. So it's gonna be like D plus 1 times I minus 1, because each one can have like all possible values. So yeah. So if you think about it like that, this Kronecker product will give us this size vector. And then this is yeah. And we denote this ugly part as just AI. It's called accumulator. And so it's just also like just prettifying this ugly part. And because this doesn't depend on the challengers, we can pre-compute them, because this doesn't depend on the verifier's input. So the main idea is, yeah, we just pre-compute all these and maintain this instead of the evaluation points. So this is gonna be, as we learned, it's gonna be, we need only what, 2, we need this size pre-compute, and this can, let's say, go up to like L over 2, or the number of iterate rounds we want to do using this protocol. So let's say if we denote it as L0, we need like.
Sure. So the A term inside the PK, right?
A term is
Inside we have a PK.
Yes.
PK can be different according to the witness. So I mean the public input and witness change, and PK will be changed.
In this part, what will change? Like, so this is Boolean hypercube. This is Boolean hypercube.
Yes, yes.
This is evaluation domain.
Yes. So in order to be pre-computed, the data should be available before proof generation, or maybe witness. So the pre-computation does the pre-computation depend on witness? Because it seems that
yeah, you need basically this polynomial, right? You need this.
Yeah. Then
if polynomial changes, obviously we need to they get kind of different pre-compute, you can say.
Yeah. How do we say it is pre-computed? I mean, so the variable PK is determined after witness generation. The
So-
MA is part of proof generation.
But it's like it can be computed before the Sumcheck protocol.
Oh yeah, I agree that. But if you think of it as an entire proof generation, it's going to be also part of proof generation. So I mean, my question is, this pre-computation can be reusable, or
So I guess there will be multiple verifiers. I guess that's the point. So for one proof, let's say there is multiple verification is done. Maybe that's the case.
so verifier has a benefit then? Using that?
No, prover can use this for multiple verifier, right? Because it doesn't depend on the challenge from the verifier.
I see. So prover prove this, and you use pre-computation, create proof, and verifier also use that, make verification much faster.
No, verification will not use this.
Oh, then who's going to use this pre-computation then?
The prover will use this to prove it for multiple verifiers, right?
Different challenges.
Different challenges.
Every round that can be reused.
Yeah,
kind of.
Yeah, every round it will be used.
I see.
So actually, we pre-compute for all the rounds, or all rounds we want. So
I see.
So yeah, because this vector of size d plus 1 times I, so it's going to be like the space needed for this is going to be this. And typically, and then after L0 rounds, we will go back to algorithm 1. Let's say, then it means we will need that evaluation table again. So that will need this size. So typically, this is much smaller because d plus 1 is, I guess this L0 is much smaller, is it?
You set it to L over 2, typically, right?
Yeah, let's say L over 2. Then it's gonna be what? Did I make a typo?
If these 1, then makes sense, but if these 2, maybe we assume that all the polynomials is multilinear polynomials, then this is going to be 1.
D is 2, and let's say,
Then I think left one is bigger.
yeah, I guess we can set L0 to be like small, right? Like 2 or 3, but L is like 20, right? So we can specify L0 based on like what we want.
I see. Then for the first 2 or 3 rounds, we use algorithm 3, and then we switch back to algorithm 1.
Yeah. So the main thing is, so the required space, it was like this, right?
Mhm.
But then we have this, so this size is reduced, space size is reduced roughly this times. So let's say L0 is 2, the required space is reduced by 4 times. It's like a lot. So if it was 40 gigabyte, it was 10 gig. It becomes 10 gigabyte instead.
So could we conclude that algorithm 3 compared to algorithm 2,
Mhm.
much more space-friendly algorithm, but still slower than algorithm 2, right? Because algorithm 2 can use this up to L over 2 rounds, but now it has a limited L0 and could be much slower than algorithm 2 or algorithm 1.
I think it's actually, it should be faster, I think.
Faster than algorithm 2 and 1 together?
Faster than algorithm 2, because algorithm 2 is slower than algorithm 1.
Yes.
So I think the point of this one is it's faster, but also reduces space.
I see. So it's a superset of algorithm 2.
Yeah, superset, but as you said, it can reduce only a few rounds. I mean,
but
L0 can be only like small
yeah.
number.
Up to L0 round is a superset, but between the L0 and L over 2, unknown.
Yes.
I see.
So I don't know what they mean by this. So maybe Tuncook Master can.
Because you have an interpolation.
Maybe. So yeah, instead of like the multilinear extension, we just use Lagrange interpolation. And then we have this instead. Instead of the EQ extension, we have this Lagrange interpolation. And then we just have, instead of the EQ, we have this Lagrange.
Okay, what's the benefit of this?
I think the benefit was
Computation.
So
it's
pre-computation is the right part.
Yep.
So left part is challenge dependent. Maybe EQ extension is actually, so the Tuncook is about multiplication over polynomials. If we have a lot of polynomials, it's better to use Karasuba or Tuncook.
Mhm.
I think evaluation, the multiplication over evaluation point is just could be school book. I think you mentioned above this. It looks like school book method.
this one.
No, above, like the binomial stuff. Okay. Yeah. The first information. Yeah, in the graph.
This one.
Yeah. This one looks like a school book method.
Mm,
But if you involve in like this kind of multiplication, it's always beneficial to use Karasuba or Tunku if the D is very big.
Mm.
And typically, always D is going to be larger than 5, right? We're going to have a lot of polynomials.
Yeah, actually, their mention is 5. I think one use case is 5.
Yeah, I think after 5, I think Tunku is beneficial. That's why maybe.
See. So actually, actually, in this case, they use even D2.
These two, then there's no suspect. You should use maybe Karasuba is a specialized version of Tunku. In D2K, D is equal to 2. I think we need to use Karasuba kind of approach. Because in order to compute cross term part, you don't need to actually multiply. You can use a diagonal term minus sum of product of sum and minus identity terms or diagonal terms. I think that technique, I guess.
Okay. Yeah, I'm not totally sure about this. So what?
I think we don't need to care about this because that's going to happen at the canonicalization, I think. If we generalize some multiplication, multiple
All in
multiplication,
multiplication?
yeah, then I think that's going to be automatically done, I hope.
So, so the Green's optimization, this guy is actually the guy who introduced the univariate skip. So in one of, I think this guy's paper introduced this EQ optimization and also univariate skip. So I'm just talking about the EQ case. This is much simpler. So first, this like EQ extension can be just separated into 3, like this. So the first part and second part and third part, right? So we can just decompose like this. So the difference between these 3 is like at round I, this is fixed, and this is gonna be we will gonna sum over the Boolean hypergroup of X prime, right? So we will just, so this part is actually like linear, we can factor it out. So if you factor this out, you have this. Actually, okay, this is the original formula of SI, and then we will like this, we will name this factor part, like linear part as Li. Then, and the rest part as Ti. So then Si can be written as just this. And then what we want to do is just pre-compute this, and then now the prover only has to evaluate this part only, and this is gonna be much smaller in size than the original case. So originally it's gonna be very big. So if you want to evaluate this one, this is actually maybe I didn't forget to define. So this optimization is specific to the case where GX is equals to this, where omega is already challenged from like, let's say, 3 previous like proving steps. So like in Spartan, we have like verifier already sent a challenge in the previous prover, and we want to prove over this EQ. So this is from the large, this is already large values. So this is going to be very large computation. So by pre-computing the linear part, the prover has a smaller runtime.
So is this Green's optimization is applied over algorithm, 2 and 3, over 3? Because 3 has the 2 terms.
Yeah, it can be applied over.
So then left term is already can be pre-computed. And the right term, we also can factor out the pre-computation part from that right term.
In actually here, We
Yeah,
don't
because-
have, so in the above cases, we didn't have this part, right?
Then,
The GX was just only this.
oh, okay, then we cannot use that into algorithm 3 because algorithm 3 already separate the pre-computed part from entire completion.
Yeah, so more like we can apply algorithm 3 on top of this, on top of this. So
Okay, so algorithm 3 and Green's optimization is separate one, but the motivation is same. They try to want to separate the pre-computable part from the computation.
yeah,
Uh,
so yeah, algorithm 3 can be applied on top of the Green's optimization. So
Green's have a number? Is it algorithm 5 then? Because 4 is
no, it has no number.
Okay.
So algorithm 5 is better version of Green's optimization.
I see.
So in the Green's optimization, we just rewrite this part, right? So
Yes.
we can apply algorithm 3 here.
I see.
So instead of using evaluation table, we will just use the EQ extension and evaluate on the way.
I see.
So yeah, again, similar to how we compute S1, we can compute TI1 as well using this. So we don't want to send the whole like D evaluations, and we don't need to also evaluate at this point. So evaluating is much more expensive than computing just this one, right? So the Green optimization is basically that. We just separate the linear part and then it's done. And then in algorithm 5, we split the TI again into left and right part.
Is it a algorithm 3 then?
No, it's a bit different.
Okay.
So it's splitting up this part. Algorithm 3 has no this part. This is again introduced only in this section. This is like the challenge from the previous proving step, not the sum check.
Then the one algorithm 5 tried to say is like, yeah, we have an option to apply algorithm 3 to the key term.
To this part.
Yes,
right?
yes.
So
But it's better to use algorithm 5 instead of algorithm 3 instead for that part.
no, algorithm 5 optimizes this, and then again, algorithm 3 will optimize this.
Okay. Algorithm 5 is working on the EQ part again.
Yes.
I see.
Again.
Computation part again.
Yeah. So it's just more like add-on on Gruen. Gruen like only split this one, but then algorithm 5 is we can also split this one, kind of.
With the sum together.
Yeah.
I see.
So yeah, again, we can separate into two halves. Not actually two equal halves. So one is L over 2 size, and one is L over 2 minus I size, because each round the variable is going to reduce. So we will write TI like this, and then we will pre-compute all the values, possible values up to L0. I can go up to L0. So the algorithm 5 overall looks like this. So we have the evaluation table, all the evaluation table, because we didn't apply the algorithm 5 or something yet, right? Algorithm 3 yet. We still have the whole evaluation table, and then we will pre-compute these values over all the possible. Like I think in here it assumed that L0 is L over 2. So we will pre-compute these, and then for the evaluation domain, we will compute TI. And after this round, we will compute using the
one.
No, actually it's so if you see it's a bit different. So here we are reusing this, but after I over L, I is L over 2, this is gonna become 0, right? So we don't need this part, but now the variable is gonna start reducing from this part, right? the XR is gonna be like, so the now the dimension is reduces by a number. So we will start, yeah. Yeah, so we will, so it's actually same formula, you can say, but yeah, this becomes 0. And so we,
But that's going to be expensive to compute.
this one,
No. In the first item, EQ part. I mean, so naturally, it's better to use algorithm. I mean, switch back to evaluation part instead of computing on the fly, because it seems to compute EQ part on the fly.
it actually always uses the evaluation table, right? Evaluation table is used for the latter part, but
I
we
see,
need to
I see.
efficiently compute the EQ part as well. So that's why we are pre-computing these.
Then I thought that this algorithm 5 is a technique to apply on the EQ part,
Mhm.
but it's somehow it's kind of mixed. It's based on the assumption that we are going to overall using algorithm 1, which is like computer evaluation or make using of evaluation table.
Yeah, the focus is focus of algorithm 5 is only this one. So there's algorithm 6. I think it will use the other ones for here.
I see.
So for simplicity, this part is
I see,
always
see.
in algorithm 1.
I see.
So yeah, with that pre-computation, it's gonna be the EQ part is gonna be much cheaper. So that's the main idea. And algorithm 6 is combining the small value optimization.
What is small value optimization?
That's so increasing the number of small values, right? The small value computations in the algorithm 4 or 3.
I see.
So a small value optimization is just increasing number of SS instead of LL.
I see.
Yeah. So if you combine, yeah, it's kind of same. Instead of the right part, we just use the accumulator.
Mhm.
And it's actually using algorithm 4, right? We are using the Lagrange interpolation.
Mhm.
And then we will use the expanded EQ to compute the accumulator. This is the formula, right? It's just, this is the formula for algorithm 4, but with this part is a bit different. Yeah. That's the main idea.
Okay. So anyway, before algorithm 2, we have a lot of optimization, but after algorithm 2, we go back to algorithm 1 again.
Yes, but in this case, this EQ poly optimization is for all rounds.
I see. So Gwen's optimization will be applied to entire rounds, but SVO is applied up to algorithm 2. Depending on the which 0, but
Yeah, up to some rounds.
I see.
But yeah, I'm not sure. So Green's optimization only applies to this form, right? But I'm not sure if Weir has this form of Sumcheck. I'm not sure the Weir's Sumcheck form. Like, does the Weir's polynomial have EQ extension in it?
Oh, yeah, I think so, because I think the difference between stir and word is difference is between using a quotient polynomial or Sumcheck part. So in order to avoid quotient polynomial, they use Sumcheck.
Mhm.
And I think, yeah, can be wrong, but I guess that because they're using Sumcheck, so EQ extension probably appear in the word.
I guess Sumcheck, I mean, for quotient is basically same as zero check.
Yeah, so instead of using quotienting, maybe and quotient polynomial, they're going to use Sumcheck, but in stir, so because it's the least decodable, there are a lot of possible polynomials. And in order to make it one, they use quotienting inside stir. But instead of quotienting, I remember it uses Sumcheck to make it this decodable to unique decodable.
Yeah, so I'm just worried, what if the Sumcheck is of this form, right? Just normal without each extension.
Yeah, we need to double check, but I guess, yeah, because I remember the general overview of the sum check part.
Mhm.
If you don't have each extension, sum over something could be 3 minus 3 or 4 minus 4. Because if we have a EQ, we can guarantee that all the terms 0 and 0.
Mhm.